Thanks for Chair's kindly introduction. Good morning, everyone. I'm Yuqi Hong from National Tsinghua University from Taiwan. The topic of my presentation today is more localized piezoelectric resonator design and implementation for electrical current sensing. And my advisor is Professor Sheng-Shian. This is my outline today. I'll begin with an introduction to MEMS sensors, then followed by an explanation of the working principle of my design. And finally, I'll present the experimental results and conclusion. And now let's begin. Recently, with the development of IoT, sensors are becoming increasingly important. In the field of sensors, MEMS technology plays a crucial role. MEMS sensors can be applied in various areas, such as biology, environmental monitoring, and even inertia. In our future pursuit of energy efficiency, current sensors will play a key role in monitoring power supply usage. Due to energy consideration, I selected piezoelectric transduction as the mechanism, as it offers the advantage of lower power consumption. So my research aims to design a resonant type current sensor based on piezoelectric transduction. The next part covers the working principle and the device fabrication process. A typical piezoelectric resonator consists of 3 layers: metal, piezoelectric material, and metal. This kind of structure tends to suffer from a low quality factor. However, adding a layer of single crystal silicon beneath the structure, known as the teapot structure, can enhance the quality factor due to the material property. Additionally, we introduce another approach called the support transducer to further enhance the quality factor. This approach involves combining the resonator with an additional Q-tank. The support transducer uses a teapot structure and operates in length extensional mode. The center disk, made of pure silicon, operates in contour mode, which provides a high dynamic mass. Hence, a single resonator is composed of 3 support transducers and a central tank. And I'll begin with the basic component, the resonator. Since the resonator in my research is a composite structure, so it's crucial to ensure that each element operates at a similar resonant frequency. Finite element method simulations are used to analyze the response. The results show that after careful design of the sub-elements, the composite structure exhibits a resonant peak with minimal energy loss. And moving on to my design, the device is a coupled resonator consisting of 2 identical resonators and connected by a carefully designed coupling beam. Based on the wave propagation theorem, the coupling beam is chosen to be 3/4 of the wavelength to enable the 2 resonators to exhibit 2 modes. After coupling, it becomes a 2-degree of freedom system with 2 modes. The first one is in phase, and the second one is out of phase, as shown on the left-hand side. The frequency difference of the simulation result is around 95 kHz. The kappa value, defined as the frequency difference divided by the resonant frequency, determines the sensitivity according to the mode localization theorem. The kappa value from simulation is around 9.3 M. Typically, the smaller the kappa, the higher the sensitivity. However, if it's too small, it may become difficult to distinguish between the 2 modes. Lastly, mode localization is a vibration phenomenon that occurs in a 2-degree of freedom system. After solving the motional equation, we obtain 2 eigenvalues representing 2 resonant frequencies. Each resonator has these 2 modes, and their amplitude are identical. if they exhibit ideal symmetry. Unlike typical sensors that focus on frequency shift, mode localization uses the output amplitude ratio, AR, between the two resonators as the sensing metric. So there are two amplitude ratios, AR1 and AR2, corresponding to the two modes. When the symmetry is disrupted, the output amplitude ratio changes dramatically. Now let's introduce the sensing signal, the DC current. There's a heating path on the support transducer of the resonator. The current generates heat through dual heating. Because the Young's modulus of the material is temperature dependent, the stiffness of the heated resonator changes. So this introduces asymmetry, leading to the change of the output amplitude ratio. After briefly introducing the working principle, the next part will cover the fabrication process. The device was fabricated using our in-house process with a total of 5 masks. The material and the thickness of the stack layers are shown at the bottom right. The SEM image displays the sensing resistor and the stack layer. Finally, I'll present my measurement results. I operate the device using a 4-port topology, and it's characterized using a network analyzer. It indeed has 2 modes. The first one is in phase, and the second one is out of phase. The response of both modes are consistent with the simulation one. The frequency difference is 99 kHz with a 4% error relative to the simulation one. Next, we present the output of each resonator. I chose Y21 and Y41 to represent the output of resonator 1 and resonator 2, respectively. And it can be observed that the amplitude of the 2 modes are not identical, which is attributed to process variation. The next part involved verifying the mode localization phenomenon. I used the power supply to introduce a DC current, and it can be observed that after introducing the target signal, both the amplitude and the frequency change. The frequency are all shifted to the left because the temperature coefficient of frequency, TCF, of the device is negative. And let's zoom in the first mode of the first resonator as a demonstration. The rate of change in amplitude is around 26%, while the rate of change in frequency is only 0.12%. The significantly higher rate of change in amplitude compared to frequency highlights the benefits of mode localization. We introduced a parameter from other group called the calibrated index. It's defined as the difference between the initial and final values, and then divided by the initial values, resulting in a unit list. After recording and post-processing the data, we can plot this graph. The calibrated index has a squared relationship with the input current, as dual heating is also related to the square of the stiffness variation. With an input current of 50 milliamps, the calibrated index of amplitude ratio is 65 times greater than that of frequency, indicating that using amplitude ratio as an output metric is more sensitive than frequency shift. And the conclusion part. In this research, we successfully combined piezoelectric transduction with mode localization effect for current sensing. And next, one of the benefits of using dual heating as the sensing mechanism is that it provides a squared relationship between the sensing current and the output index, resulting in a greater sensitivity compared to linear sensors. And finally, we verify the mode localization phenomenon, demonstrating that using amplitude ratio results in a 65 times enhancement of the calibrated index. Lastly, I would like to thank NSTC, TSRI, and CNMM from National Tsinghua University in providing the fabrication facilities and research funding. And that's all. Thanks for your attention.